Okay, so let's go through this in-class assignment and make sure we all know the correct answers here. So question 1, what is the name of this molecule there? That would be an allyl or an allylic cation. I did not discuss a bool right there, so that's technically the correct answer. If I have two resonance structures, this represents how many molecules? Remember, resonance structures are describing the same molecule, so it's just one. If you had 10 resonance structures, it would be describing one molecule. Question 4, in resonance, which electrons are delocalized? With the answer choices that you have there, that would be the pi electrons. What can the following molecule have a resonance structure? Yes, it definitely can, because that negative charge, okay, if we draw it out here, that negative charge on this carbon right there is negative because it has a lone pair. So that lone pair can come down and then go like this. And the structure now has the lone pair on that side, the double bond there, and now that's going to be negatively charged over there. So yes, whenever you have lone pairs adjacent to double bonds, there's going to be resonance structures. So for example, if you had, let's say, something that looked like this, that's negatively charged carbon with a lone pair, you see that that carbon is adjacent to that carbon. And this carbon right there has a double bond. So we can just take that lone pair and resonate it in over like that. And now our resonance structure would look like this. Double bond there. Now, with the resonance structure up top, how many lone pairs did it start with? It started with 2 of them. But as the green arrow right here is showing us, I'm taking 2 electrons in that pi bond and I'm going to move them right there. Now I have a negatively oxygen atom that has a single bond with 3 lone pairs, so that has to be negatively charged. And when we take a look at this carbon right here, it was negatively charged there, but now what does it look like? It's neutral. Because remember, when you have an anion, how many hydrogens are there? There's a hydrogen atom right there. And that blue hydrogen is still there. Okay, question 6. Is this a valid resonance structure? Yes, it is. Okay, number 7. So what's the first rule that we're supposed to remember? All atoms, or the resonance structure that has the most atoms that have a full octet or a filled octet, are more significant than those who do not. So when we take a look at molecule 1, we can see that the carbocation right there only has 6 electrons around it, and every other of those atoms, the oxygen right there, has an octet. How do I know that oxygen has an octet? So when we zoom in, how many lone pairs does that thing have? It has 2 lone pairs. And then the oxygen with the negative charge, that's going to have 3 lone pairs. So when you focus in on this oxygen right there, you can see that there's 8 electrons, 4 in lone pairs, and then another 4 in the 2 bonds. So let's just circle in blue what atom does not have an octet. It's that carbon there. And in molecule 2, you will see that all the atoms have an octet, excluding the hydrogens because that's not possible. And then in molecule 3, every atom there also has an octet. So based off of rule 1, this molecule 1 is going to be the least significant because not all atoms have an octet. Molecules 2 and 3 do. So now we need to break the tie between 2 and 3, we have to go to rule number 2, which says the molecule that has the least amount of formal charges will contribute to the resonant hybrid the most. And we can see that in molecule 3, there's 2 formal charges, and in molecule 2, there's 0. So that makes that the most significant, and this would be the second most significant. So that would be 2, 3, and then 1. So answer D would be the correct answer choice. All right. Okay, the nanotexane. Let's take a look at this one. So how many total lone pairs are on the eyeballs or the oxygen atoms of the texane? When we take a look at that texane, the 2 oxygens, which are the eyeballs there, those are 2 oxygen atoms that are neutral with 2 bonds. So that's just naturally 2 lone pairs each. You could draw like that if you like. Okay, the next question. What orbitals are used for the bonds between the eyeball and the mouth of the texane? So this carbon right here that I'm just circled there, that's supposed to be this cigar, just for kicks and giggles, okay? So the mouth is that carbon right there. So if we take a look, what the question is asking is it's asking the bond between the oxygen atom in the eyeball and the mouth. So we're looking at that bond. Or we could be looking at that bond. Either one, it doesn't matter because they're the exact same. So we're looking at that bond there between the eyeball and the mouth. Now, in order to figure out what orbitals are involved, we need to know the hybridization state. And the oxygen atom right here, we see that there are 4 electron groups around that oxygen, and the 2 lone pairs are localized. There's no resonance structures. So there's 4 groups around the oxygen, which means it's going to be sp3 hybridized. When you take a look at the carbon atom right here, you will see that there's 4 bonds. It is neutral, so that would have to also be sp3 hybridized. So what's going to happen is those 2 atoms all have their sp3 hybridized. So if I take a look at the oxygen atom, it's going to have the 4 sp3 hybridized orbitals, and I'm going to do those in green. So we're going to have 1 there, 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 and there. Now, when we take a close look at that oxygen atom right there is forming a bond with a carbon. And so I'll draw the carbon here, like that. And what orbitals does the carbon have? Well, it also has 4 sp3 hybridized orbitals. And so that interaction right there, shown in blue, that's the bond that's forming between the oxygen and the carbon. So in blue, that overlap that you're seeing there, that blue right there, that's responsible for that bond right there. And then the oxygen atom right here, let's find a different color here. Yeah, let's take a look here. Now look at this. This oxygen atom right there has a bond right there to another carbon. So we could represent that orbital right there, here. Well, that's bad, isn't it? That's bad as well. What am I trying to do here? So there's some overlap there with a carbon. So that's that bond right there. So where's those lone pairs on the oxygen? Those lone pairs are right there. And what are those orbitals right here? What type of orbitals are those that the lone pairs are in? Those are sp3 hybridized orbitals. So back to the main question here. What orbitals are used to form that bond? You could annotate it like this. You have a oxygen atom, a sp3 hybridized oxygen atom forming a bond with a carbon atom with its sp3 hybridized orbital. Does the Texan have any terminal alkynes? This guy right there is internal because it's sandwiched between a carbon and a carbon. But this one right there would be a terminal alkyne because what is the triple bond sandwiched between a carbon and a hydrogen? So that definitely is a terminal alkyne. What are the hybridization states of carbons 1, 2, and 3 and the sulfur atom? So let's zoom in there. So the sulfur is in group 16, so it has 6 valence electrons. I count 2 there, 3, 4. Let's see there. And then the hydrogen atom right here coming off 5. So 6 minus 5 equals plus 1. So plus 1 for the sulfur, formal charge, and then the nitrogen atom, nitrogen 5, has 4 bonds. So nitrogens with 4 bonds is a plus 1. Let's see. How many hydrogens are on the Texan? Ooh, that's not hard, just it's a big molecule, so we have to be very, very, very careful when we're counting. So let's just zoom in and label them in purple, but I'm not going to draw out the hydrogens just because it takes too long. So I'm just going to do tick marks. And let's see if that works here. So we have 3 here, coming off of there, 2 there, definitely that one. 1 right there, there and there, 2 there, 3 there. You know, we have time. Let's just draw in all the hydrogens so there's no mistakes. And we have 2 here. Hydrogen there, hydrogen there. Have that one. We have 1 coming off of there. 1 there. 3 coming off of that. There's a methyl. There's 3 coming off of that one. Let's clean that one up. Hydrogen. Is there hydrogen on that carbon? No, there's not, because there's already 4 bonds. 1, 2, 3, 4. So we have 3 coming off of here. we have 3 coming there. What about that carbon? How many bonds are on that one? That is bonded there, 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 and there. So that already has 4 bonds. So there's no hydrogens there. But if we come here, there's going to be 2. That one's going to have 2. And this one right there, the drawing's getting small now, but that's going to have 2 as well coming off of there. So there they are. Now if we just add them all up here, I'll just mark them off as I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, and 37. So I count 37. And I hope I didn't miss any. So we'll say 37 right there. And if I missed any, I'm pretty sure you guys will be able to make me aware of that. But wait, did I miss one? I think I did. Let's see. I'm just double checking here. And we already talked about that one. That has 4 bonds to it. Okay, so there's no hydrogens coming off of that one. So we're good there. Okay. Draw 2 resonance structures here. Look, and we did this one in class, but since we're here, let's just do it real quick. Okay. So there's our double bond. You know, I don't like drawing it that way. I'm going to redraw like this. Okay, I don't know, that's just easier for me to do. Now, oxygen 1 has 2 bonds and is neutral, so it has to have a lone pair, and that has to have a lone pair. So in order to draw a resonance structure, we need to realize that we have a double bond adjacent to a lone pair. When that is the case, we can have resonance. So we can say that this lone pair is going to come down like this. And then the pi electrons in that double bond are going to go there. And when we do that, we have 3 lone pairs there, 1 lone pair there, double bond, so that has to be plus, and I did not touch that double bond right here. That's still present. Okay? So that's one resonance structure that we could do. If I redraw the starting molecule here, I could have drawn another resonance structure like this. Pi electrons next to more pi electrons, we can have resonance structures. So those pi electrons can come in between. There's the lone pairs already, and then those pi electrons can come there. And so we still have those lone pairs. We have 3 lone pairs on that oxygen now. I moved the double bond right there. So now we just need to reassess our formal charges. So we clearly can see that that had double bond character at one point, now a single bond. So we know we have to figure out the formal charge of that oxygen atom, and that's going to be -1. This carbon right here has now lost a double bond. You see how there's a double bond there, but now it's gone. How many hydrogens was on this carbon right there? It had one. So it still has just one hydrogen because atoms don't move in resonance structures. So how many groups does that carbon have? It has 1, 2, 3 electron groups. It has 3 bonds. So that makes that carbon a +1 when you calculate its formal charge. We could also draw another resonance structure for this example here. What if we start with our original? There's our double bond. Could we have also drawn a resonance structure that looks at the carbonyl piece? And just the carbonyl piece, yeah. We have pi electrons here that can go on top of that oxygen atom. And when that does that, we would have an O. We have 3 lone pairs now. So that's going to be negatively charged. When we do a before and after check, we see that that carbon right there has 4 bonds. But now we look at that carbon and that only has 3 bonds. So that would have to be a +1. Okay, let's take a look at this one here. Now, what we can do here, we see that we have double bond adjacent to a double bond. Whoa. So when I double tap that, why does it do that? So let's move those pi electrons right there. Or you could have drawn it like this. It doesn't matter, but I'm taking those pi electrons and putting them between the 2 carbons. And then I'm going to take those pi electrons and move them to the oxygen. Now let's draw what I just showed you with those green arrows. I'm going to have the oxygen there. Like that, we still have the double bond. I took that double bond and moved it there. And then my oxygen atom is now going to be negatively charged. And so what's the formal charge on that guy now going to be? It now only has 1 hydrogen attached and 2 bonds that are shown directly. So that has to be +1. Now from that resonance structure, what could we do? We could, let's see here, we could go like this. We could take these pi electrons, which are adjacent to a carbocation, we could take those pi electrons and move them in between. And if we do that, we have the double bond still there. We still have the negative charge. And now we put the double bond there. So that formal charge now no longer exists because that carbon, which is that one, has 4 bonds. But now what has happened here? That carbon right there only has 2 hydrogens coming off of it that aren't shown. And now it only has 3 bonds, so that has to be a positive. Now, could we draw another resonance structure? Sure. And this one's going to be a little bit of a crazier one, but still valid. We have lone pairs adjacent to a double bond. So I could bring those down. Those could then come and move here. And then those can move back. So now in that one, we have 3 arrows, which is also valid. And so I didn't do anything with that negatively charged oxygen. I still have 1 lone pair there, but then I made a double bond between the oxygen and the carbon. I took that double bond and moved it there. And then I took that. So we can see where the electrons are coming from, but what am I missing? I have an oxygen atom right here. That has 3 bonds to it with a lone pair, so that makes that positive 1. So those are some resonance structures that you could have drawn. A very simple one that is 100% valid. Another one that you could have drawn. Another good one would be I need that one. Could have taken that lone pair there, brought it down, brought it like that. And that resonance structure would look something like this. Like that. Okay, next one. Being able to look at the structures and just showing where the electrons go. So a good starting point would be, how many carbons do I have? 1, 2, 3, 4, 5, and 6. So draw 6 carbons, because remember, atoms don't move. So 2, 3, 4, 5, 6. There's my zigzag. And then looking at the arrows, if that's carbon 1, and that goes all the way to carbon 6, where did the electrons go? That double bond moved between, or from 1 and 2 to between carbons 2 and 3. So that double bond moved there. And then the double bond between 3 and 4 moved between 4 and 5. And then the pi electrons between 5 and 6 just added a lone pair on carbon 6. And so that's where all the electrons have moved. And now, after they've moved, we have to reevaluate formal charge. Carbon 1 is neutral on the left, but positive on the right. And then we look at carbon 6 was neutral on the left side, but has to be negatively charged on the right side. Because how many hydrogens are on carbon 6? So there's still 2 hydrogens there. So when you look at carbon 6, it fulfills the octet, has 8 electrons around it, but only has 3 bonds. So when you calculate the formal charge of 4 minus 5, that would be a negative 1. Now for this nitrile, and that's called acetonitrile, we know that there's a lone pair right there. Because a nitrogen with 3 bonds, and that's neutral, has to have 1 lone pair. So now we are looking at what has happened. I've taken some pi electrons and I've moved them to the nitrogen atom. So the purple lone pair was already there, and then I took 2 electrons from the pi bond, put it there. So that would make the formal charge of the nitrogen negative and the carbon positive. Okay, so the last question here. We want to rank the following from least significant to most significant. So we have to highlight the fact that it says least to most. Make sure we got that. So looking at rules number 1, we know atoms that have an octet. So in order to do that, you have to make sure you understand that a neutral oxygen with 2 bonds has 2 lone pairs. And a nitrogen atom with 3 bonds and neutral has 1 lone pair. So now when you count the nitrogen, you'll see that there's 80 electrons. And when you count the oxygen, there's 80 electrons. So if we do that analysis there, and then that anion, that's going to have a lone pair there. Okay. So I'm just going through here, making sure I have all the lone pairs. An oxygen with a single bond would have to have 3 lone pairs, and then a nitrogen with a plus charge, well, that has 4 bonds, so that can't have any lone pairs. Okay, so rule 1, look at the atoms. Do they have octets? And when you take a look at this first molecule A, there's 8, 8. So every atom here, that has 8, that has 8, that has 8. So let's do this one right here, that carbon. How does that have 8 electrons? Well, it has a hydrogen there. So there's 4 electrons in that double bond, 2 electrons in that bond, and then 2 in that bond, making that a total of 8. So A has an octet. B has an octet. So I'm going to just say octet, octet, check, check. No, this has a carbon that has no octet. And then D has an octet. Every atom has an octet. So from that rule 1 analysis, what we can say is that C is the least significant. And so that would go there. That's the least significant. So now so we can kind of scratch that guy off. We already have that accounted for. Now we have to make a judgment call between A, B, and D. Okay. So all of them have an octet. So what's the rule number 2? Formal charges. Okay. So clearly A has no formal charges, B and D do. So we can, from that analysis, we can say there. A is the most significant. Now between B and D, what difference do we have? What differences do we have and what's the same? Well, we see a nitrogen and a nitrogen both with a positive charge, so that's a wash. But look at what's different though. We have a negative charge on a carbon versus a negative charge on an oxygen. And we've learned that oxygen atoms are more electronegative than carbon, so it can tolerate a negative charge better. And so that's going to make D more significant, which then by default would make B less significant because it has the negative charge on the less electronegative atom. So B is going to be less significant and D is going to be more significant, giving us that order there. Now draw the resonance hybrid for the amide molecule above. Well, when we do that, we want to take a look at all the resonance structures that we've come up with, and we're looking for which atoms have negative formal charges, which bonds have positive charges, which ones have double bond character, triple and single bond character. And so when I draw the resonance hybrid, I'm going to have the connectivity all the same, guys, like this. Okay, and then we have a bond to oxygen. Now, taking a look at the oxygen atom, we see that there's double bond in A and then single bond character in C and D. So we're going to leave the carbon-oxygen bond as a single, but we're going to do a dotted line to imply that it's partially double bond character. And it's never really purely single bond. Now, we can also take a look at this bond right here. Let's zoom in. This nitrogen-carbon bond right there. Do you see how it's single bond there, but double bond there? So all we have to do is just draw a dotted line that represents that partial double bond character. Now, we see in A, there's a double bond, but in B, it's a single bond. So we just represent, hey, that's going to be that. What about this bond right here? Single, double. So we'll just represent that with a double bond character. Now when I take a look at that carbon-nitrogen bond, single, single, and single and single. So that just stays straight up single. Now that we have our double bonds, partial double bonds there, now we just have to figure out the partial charges. Okay, and so we see a full-blown a positive charge on the nitrogen. Okay, full-blown positive on a carbon, and a full-blown negative on the oxygen. But sometimes the oxygen is neutral. So the way that we draw it on a resonance hybrid is that the oxygen atom has a partial negative, and the nitrogen has a partial positive. Then there's another partial negative, because when you look at that carbon, it's neutral, there it's negative. So there would be a partial negative on that carbon as well. And that should be it.